Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and we're going to continue our discussion on ordinary differential equations. And in particular, last lecture we talked about a solution method or analytical solution method for when we have a system of first order ordinary differential equations, or first order or system of first order IVP, initial value problem. And we confine that method to the very simple case of when the system of equations is linear, constant coefficient, and homogeneous. And we mentioned that that methodology, that particular analytical technique, would only work in that event. So what happens when the system of equations happens to be variable coefficient or non-homogeneous, or even worse, what happens when it's nonlinear, or at least one of the equations is nonlinear? Then we cannot construct a system based on these state variable representation with a matrix and a vector that contains the independent terms, and the method that we learned doesn't work. So as we did for single equations, we are going to have to construct a technique or formulate a method by which we can approximate the solution. And the approximation of solutions of the system of equations, systems of ordinary differential equations, follows exactly the same procedure as it does for single initial value problems. So essentially, you discretize the time into little pieces. We call these pieces time steps, and we go through an approximation that relies upon a Taylor series expansion of the derivative, and then we can construct higher order representations of these approximation, and depending on the construction or depending on the order of approximation, we have a method that converges faster to the right solution than others. So basically what we can do is use an extension, a very simple extension of the methods that we already learned, namely the predictor corrector scheme, the Euler, the modified Euler, the Hoynes method, the Runge-Kutta method, and other methods that can actually be framed within the same context. We can just extend these very simply and then apply them to system of equations in a very straightforward manner, that is. So what we're going to do today is just look at how we go about these extension and then work on an example. So this is modeling methods in ME, and we are going to talk about numerical solution or numerical approximation solution schemes for systems of first order ODEs. All right, so let me summarize briefly what I just said. So the analytical method previously described is limited in its application to systems of ODEs that are, first of all, linear, constant coefficient, and homogeneous. So it becomes necessary to formulate an approximation scheme that can be applied to more general cases. So, in general, we can express a linear variable coefficient. So let's just keep it linear, although this methodology that I'm going to discuss also works for nonlinear, but let's now extend it to variable coefficient and also non-homogeneous system of ODEs. We can express the system as follows. So y dot of t, which are the state variables, the unknown functions that we're looking for, is equal to this state matrix A, which is now a function of time, or where at least one of the coefficients of this matrix could be a function of time. That would make the entire system variable coefficient, times the state variables, or the unknowns, plus a vector of independent terms G, which will make the whole thing, if at least one of the members of this vector is different than 0, then it will make the entire system non-homogeneous. And it could also be a function of time with initial conditions given by a vector of the state variables at time equals 0 given by some initial conditions. Now, the solution of this system may be approximated using a simple extension of the numerical schemes formulated for single first order ODEs. And those are, at least the ones that we formulated in class, the predictor corrector scheme, which I mentioned several times that these are not limited to the ones that we described in class. There are many more. We start with the basic one, which is the Euler's method, which, remember, is order delta t accurate, so it converges as fast as delta t. Modified Euler, which is order delta t square. The Homogeneous method, which is also of the order of magnitude of convergence of the delta t square. And finally, the Runge-Kutta, which happens to be order delta t to the 4 accurate. I mean, that is the order of the truncation error, meaning that the method would actually give you an error that is proportional to delta t to the power 4, or it converges. As you change delta t, it will be 4 times, or in the order of magnitude of the power of 4 of that, as the error will decrease. So, if you recall, a single initial value problem is given by dy dt y at t, and a single initial condition y at 0 is equal to y naught. Now, the system of ODEs may be written as y dot at t, which is the derivatives of each of the state variables, is equal to some vector of functions of y and t, where y, remember, is a vector. Now, if the system is linear, as we're suggesting for this particular application, then remember y dot is equal to this matrix times the vector of state variables or unknown variables plus the known vector of independent terms, and therefore we can just simply encapsulate the functions y of t as this entire right hand side, which happens to be a vector because this is a matrix times a vector makes up a vector. So it's a vector a of t, y of t, plus g of t. In general, we can just express these functions on the right hand side if we wanted to express a system of equations like this, and just simply implement the numerical schemes exactly the same way as we did before, looping over the state variables, that would be y1, y2, so on and so forth. So we would have to loop at every time step, So remember, we in the implementation of these techniques before, we constructed an algorithm where we loop over the time steps, over n time steps. Now within the loop of time steps, we're going to have to loop over all these variables, state variables, so that we can solve them all simultaneously within the same time step, and then we can advance to the next time level. All right, so this is a very simple approximation, which I will demonstrate for you in a MathCAD file just in a minute. But let's work on an example, and while doing so, we're going to try to solve this problem analytically, because this is something that we didn't practice last time when we formulated these methods, these analytical methods. So, an example: find the exact solution and numerically approximate the following system of ODEs. So we have a system that has two equations and two unknowns. So we have dy1 dt is equal to minus 3y1 plus y2 of t, and dy2 of t is equal to y1 of t minus 3y2 of t. All right, notice that the system is linear, homogeneous. There's no independent term. Everything is multiplying the unknown state variables. Constant coefficient. System of k equal to first order ODEs. So we have two first order ODEs. They're coupled. As you can see, you cannot solve the first equation without knowing y2. You cannot solve for y2 without knowing y1. So you have to solve them simultaneously. So therefore, and then with initial conditions, y1 of 0 is equal to 2, and y2 of 0 is equal to 0. So we can express this as a vector y0 equals to 2 and 0, with two elements, obviously. So because the system is linear, homogeneous, constant coefficient, and because it is well posed, the system of equation is imposed, and the proper amount of initial conditions is imposed, then the analytical solution method applies. So therefore we can find an exact solution. So let's express this method as, or the system as, express as y dot of t equals to a y of t. And in this case, the matrix of coefficients, of constant coefficient, in this case will look like minus 3, 1, 1, minus 3. So minus 3 is the coefficient that multiplies y1 on the equation, on the first equation. It's coefficient 1, 1. Coefficient 1, 2 is 1. Coefficient that multiplies y2. And as you can see, that's the order in which things are stated here. And then we're going to use these matrix to solve the eigenvalue problem. Solve the eigenvalue problem that says that the determinant of A minus lambda I is equal to 0. So remember, this came from the fact that we are going to try to look for a non-trivial solution of the system of equations. Remember, if we look at the system of equations, a natural solution is that y is equal to 0, because if y is equal to 0, then whatever A is times 0 should equal the derivative of 0, which is also 0. So it's satisfied, but it will not satisfy the initial condition. So we have to look for a solution of this system that is non-trivial. In order to do that, well, either we find that we get that the coefficients are 0, or that the determinant of this expression is equal to 0, such that lambda, as we know, are the eigenvalues, and lambda times the identity matrix, given in this particular case of the identity matrix is a 2 by 2 matrix, it has to match the order of the matrix A, should be lambda 0, 0, lambda. Okay, so we're going to subtract this matrix from this matrix, or so this matrix from this matrix, and we're going to calculate the determinant of that. So basically, what we have is that the determinant of the matrix minus 3 minus lambda 1, 1 minus 3 minus lambda should be equal to 0. And a 2 by 2 matrix calculating the determinant is very simple. We just basically multiply the diagonal and subtract the multiplication of the off diagonal. For a 3 by 3 matrix, the determinant would be, we can augment the matrix with 2 additional columns, and then take the multiplication of the diagonals, and then take the negative of the multiplication of the counter diagonals, and so on and so forth. For a 4 by 4 matrix, it's a lot more complicated, but we can always do it in terms of some matrices like this. So here, the equation that we're going to be solving for is minus 3 minus lambda times minus 3 minus lambda minus 1 times 1 should be equal to 0. So that is the eigenvalue equation. That is, if we multiply these through, we get 9 plus 6 lambda plus lambda squared minus 1 is equal to 0, or simply lambda squared plus 6 lambda plus 8 is equal to 0. And this is a quadratic equation which should yield, so we basically calculate lambda 1, 2, the two solutions of these quadratic equations, which, by the way, remember, eigenvalues do not necessarily have to be real. We can have complex eigenvalues. Let's see how it works in this case. So minus b plus minus square root of b squared minus 4 times 1 times 8 divided by 2a, which is 2 times 1. And so this yields lambda 1 equals minus 2 and lambda 2 equals minus 4. They're usually, these are the eigenvalues. And usually, because of convention, it's appropriate to order them in descending order. So as you can see, the largest number, not in magnitude, but the largest number in the real terms is the first eigenvalue. So this is usually sorted from max to min, as shown in this case. All right, so we have the two eigenvalues. Now we have to find the eigenvectors. The eigenvectors. So we have an eigenvector corresponding to the first eigenvalue, and we have an eigenvector x corresponding to the second eigenvalue, which are basically the directions that correspond to this special value that makes the solution be non-zero or non-trivial. So basically that would be a minus lambda I times x is equal to 0. So that was the original eigenvalue equation, from which we determined that the determinant of these had to be 0 in order to find a non-trivial solution. So for the first eigenvalue, for lambda equals lambda 1, which is equal to minus 2, we have minus 3 minus minus 2, 1 times then 1 minus 3 minus minus 2. This is the matrix A minus lambda I times x1, x2 of the first eigenvalue should be equal to 0. So that yields minus 1 times 1, or 1, 1 and minus 1 times x1, x2, 1 should be equal to 0. So minus 3 plus 2, minus 3 plus 2 on the diagonal. So that yields a system of equations that says minus x1, so the first row times the column vector is minus 1 plus x2 equals 0. And then this one is x1 minus x2 equals 0. So as you can see, these are basically a repetition of the same two equations. So this is the same equation, just negative. So these are linearly dependent equations. So these are the same equations. Just right here, notice that these are the same equations. So this system has infinite solutions, but that's fine. So what you can do to fix at least one of the solutions, because at the end of the day, remember, we're going to pose the solution of the system as a general solution with a constant of integration. So basically we can just fix one. Let's say x1 is equal to 1. So if we fix x1 to be 1, then x2 has to be also 1. Right? For both equations. If we fix x1 to be 2, then x2 has to be 2. Right? So as you can see, the x2 is linearly dependent on x1 because the two equations are exactly the same. So basically the first set, or the first eigenvector is equal to 1, 1. And you will see that basically later it will be just times a constant. So basically we can add a constant in front of these and it will always work out the same. If we say that x1 is equal to c, then minus c plus x2 is equal to 0, x2 is also equal to c. So basically the eigenvector is a direction, 1, 1, multiplied times a constant. So since the eigenvector represents a direction or rotation, essentially adding a constant to it doesn't really matter because the direction should be just a unit vector. And in essence, we should also take the square root or divide each of these elements by the square root of the magnitude to make it a unit length vector. But it's not necessary because at the end we're going to multiply it by a constant, as you will see. So let's look at what happens when we use the second eigenvalue. So if we say for lambda equals lambda 2, which is equal to minus 4, the system would look like minus 3 minus minus 4, 1, 1, minus 3 minus minus 4, x1, x2, the second eigenvector is equal to 0. That would be 1, 1, 1, 1, x1, x2, second eigenvector, 0, which means that now you yield a system of equations that says x1 plus x2 is equal to 0, and x1 plus x2 is equal to 0. So again, these are the same equations, infinite solutions. And the same thing will happen if you have a system of 3 by 3 or 3 equations, right? You end up with 3 equations where one is a linear combination of the other two. So you basically have a system with infinite possible solutions. An overdetermined system. You have more unknowns than equations. So again, you fix one. So fix 1. Let's let x1 be equal to 1. And if we let x1 be equal to 1, then x2 will be equal to minus 1. So basically, the eigenvector x1, x2, number 2, is equal to 1 minus 1. So we found the 2 eigenvectors and corresponding to the 2 eigenvalues. So now we can say, combining these to form the general solution. So remember, the general solution is given by a combination of these eigenvalues and this eigenvector. So y of t, which is equal to y1 and y2 of t, is equal to c1 times the first eigenvector times e to the first eigenvalue t plus c2 times the second eigenvector times e to the power of the second eigenvalue t. Right? And that's why it really didn't matter if we fix 1 to whatever value, because it's always going to be multiplied by a constant, and it's not going to make any difference. At the end, we're going to fix those constants with the initial conditions, and the result is going to be always the same. It doesn't matter what we fix one of the elements of the eigenvector to, or if we fix the second element, it really doesn't matter. So y of t, so the general solution is y of t, which is y1 and y2 of t, is equal to the constant of integration c1 times 1 times e to the minus 2t plus a constant of integration c2 times 1 minus 1 times e to the minus 4t. So you have that linear combination of exponentials of different order as expected, because the solution of a single linear homogeneous constant coefficient IVP or ordinary differential equation will be an exponential like this. That was the premise of our assumptions to come up with this methodology. All right. So now let's figure out what the particular solution is. So in order to find the particular solution, then let y of 0, or impose the initial conditions, the given initial conditions, that y1 at time equals 0 is equal to 2, and that y2 at time equals 0 is equal to 0. And then plug that into the general solution. And remember, that would be the first equation is y1 equal to c1 times 1 times e to the minus 2t plus c2 times 1 times e to the minus 4t. So we're going to say y1 at time equals 0 is equal to c1 times e to the minus 2t plus c2, this will be 0, times e to the minus 4, 0. And that's equal to 2. Well, y2 at time equals 0 is equal to c1 times 1 times e to the minus 2t, c2 times minus 1 e to the minus 4t. So it will be c1 e to the minus 2, 0, minus c2 e to the minus 4, 0. And that's equal to the second initial condition, which is 0. So from here, remember these exponentials of 0 are all 1, so we have c1 plus c2 is equal to 2. Well, c1 minus c2 is equal to 0. And this is 2 by 2 system of equations that is very easy to solve. Well, one thing that we can do is add these two, and then we get 2c2 equals to 2, and then we can subtract the 2, and then we get 2c2 is equal to 2 as well. So from this system of equations, we can figure out very easily that c1 is equal to 1, and c2 is equal to 1. And then we plug those in back here. y1 of t is equal to, well, we go here, c1 is equal to 1 and c2 is equal to 1. So basically it's 1 times e to the minus 2t plus 1 times e to the minus 4t. And 1 times e to the, and y2 would be 1 times e to the minus 2t minus 1 times e to the minus 4t. So this will be e to the minus 2t plus e to the minus 4t. And y2 of t would be equal to e to the minus 2t minus e to the minus 4t. That's the difference between the two equations. Or we can just pack this up into a single in vector form. This will be 1, 1, e to the minus 2t, and this will be 1 minus 1, e to the minus 4t. And this is the particular solution. Particular solution of the initial value problem. Okay. This basically satisfies both simultaneously the ordinary differential equation, the system of ordinary differential equations originally given, and the initial conditions. So this satisfies this system of equations. You can test it. You can take each one of these and plug it in here and take the derivative of the first one. You'll see it matches. But it also satisfies the initial condition. If you make t equal 0, you get 1 plus 1, that's 2. And you get on the second row, you get 1 minus 1, which is 0. So it satisfies. Now, approximate this numerically. Using predictor, corrector schemes by discretizing time from time equals 0 to, let's say, time equal to 2 seconds or 2 days or 2 years, whatever unit of time we're working on, whatever these physically represent. So our final time is going to be equal to 2. So basically what we are going to do is we're going to say this is the final time. We're going to let n be equal to 1 through n, and or from 0 to n. Now we're going to modify this a little bit and start the count at 1. So for a reason that I'm going to explain to you in a minute. And delta t is going to be tf, the final time, divided by n. Okay, total number of time steps. All right, so we're going to move to MathCAD, and so we're going to start. We're going to start by this to define. All right, so we're going to start by changing the origin in this MathCAD spreadsheet to 1. And what that basically means is we're going to take this directive called origin equal 1. We can also do that through the menus. Basically stating that the arrays, the array counters are going to start at 0 instead of at 1 instead of starting at the default value of 0. So elements of an array will start at position 1 rather than at position 0. And that would make it a little bit less confusing when it comes to the fact that we have basically 2 equations in the system, and the system is we're going to loop from 1 to 2. So we're not going to have equation 0, equation 1. We're going to start at equation 1, but we cannot change the origin of the array for some arrays and not changing for others. So including the array that counts time, or the array where we store the values of time of the discretized time steps, we're going to also start it at 1 instead of at 0. All right, so we are going to define the system of equations with capital K equal 2, that denotes the total number of equations in the system. And we're going to use that in the internal loops of all these solutions, the solution algorithms. The matrix A, which is the matrix of coefficients of the system of equations, is -3, 1, 1, -3. In order to define a matrix, I say A, and in this case I'm going to say that this is a function of time, even though none of the elements of these matrix are functions of time. So basically, to generalize it, so if I want to change one of these elements and make it a function of time, I could. So I'm going to say A as a function of time is equal, and then I say Control M, and that introduces a matrix. By default, the number of rows and columns are 3, so I'm going to change that to 2 and 2. And then I can just freely enter the elements of each of these, or the values of each of these elements. And by the way, I can just multiply these times t if I wanted to, so the elements of any of these coefficients can be also function of time if I needed to be, if the given system of equations was variable coefficient. But the one that we have at hand is constant coefficient. The same thing I can do for G, the vector of independent terms, which could also be a function of time, and in this case it's a matrix also, Control M, but it's a matrix of 2 rows and 1 column. And that is a 0, 0, which makes the system homogeneous. But in general, we can implement this spreadsheet that we have here for a non-homogeneous systems with variable coefficients. Also, the system of independent, or the vector of independent terms, y dot O, is a matrix of 2 rows and 1 column, 2, 0. I'm using the tab to actually move within each of the elements of these vectors or arrays, or I can just use the pointer and the mouse. Also, the exact solution y of t, which we're going to use to compare the numerical solutions, is also a 2x1 array, given by the 2 particular solutions that we just found in the notes. We're going to define the final time, the 2, and we're going to start by discretizing the time into 10 steps. Okay, we're going to start with a very coarse discretization to see what kind of errors we get. And remember, the delta t, the size of the time step, is going to be equal to the final time divided by n, which is in this case 0.2 seconds, if these times represent second. Now, because we changed the origin to 1, we are going to start the counter, which is this range variable n, at 1. So when we actually say print n, see, I get a counter that goes from 1 to n plus 1. So we still get the n plus 1 number of time levels separated by time steps. But now, instead of starting at 0, I start at 1. Okay, and therefore, because time needs to start at 0 and end at 2, the array that holds the value of time indexed by the range variable n is going to be n minus 1 times delta t instead of n times delta t. In previous spreadsheets, we had started the origin of every array at 0, and therefore n had started at 0, so we can define t as n times delta t. In this case, see, if I print t, I'm going to get an array which, with the first index at 1, the last index at 11, starting at time equals 0, separated by time steps at 0.2, all the way to 2. If I had changed this to, if I make this 20 time steps, then this array would have 20 elements, which I can access by crawling from element number 1 to element 21. So 21 elements from time equals 0 to time equal 2 seconds. So I'm going to go back to 10 elements. It's the coarser discretization that I can. And k, which is the counter that defines the total, the number of solutions in the array, or the number of solutions of the system, or the number of equations in the system, is an array, is a counter that goes from 1 to k. It's a range variable that goes from 1 to k. So I'm basically defining the exact solution as a two-dimensional array where the first index holds the time steps and the second index holds whatever the solution is, the solution 1 or the solution 2. So basically the exact solution, yx, indexed by n and k, is equal to, I'm going to do this again, is equal to the solution y of t, but it's now t indexed by n, left bracket k. So it's the k element of this array, element 1 or element 2, evaluated at the nth element of the time array. So if I print yx, then what I'll get is a two-dimensional array. Notice in the rows we have the total number of time steps, and in the columns we have 1 and 2, denoting solution number 1 and solution number 2. So this will be the array of solutions for y1, and this will be the array of solutions for y2. If I change this to 20 time steps, then I'm going to get a 20 by 2 array, or 21 by 2 array, denoting the 21 time values and the 2 solutions. All right. So I'm basically increasing the dimensionality of the problem by 1 in this case. Now, here's the Euler's algorithm, and notice that it's identical except for the fact that I have an inner loop that loops from 1 to k. So within the loop that loops over all the time steps, n, that loops from 1 to n, I'm also going to loop internally from 1 to k, so that I can calculate the k1s, k2s, k3s, and so on and so forth, the predictor corrector parameters for each of the solutions k in the state system. So first I loop from 1 to k to fill in the first element of the vector y. So the vector y internally is the one that I'm going to return, and it's going to occupy y Euler. So I am filling out the first element of this vector for the two columns, k equal 1 and k equal 2, with the initial conditions. And then I'm looping over all the time steps, and within the loop of all the time steps, I'm looping for all the state variable solutions. And then internally in those state variable solutions, I am actually implementing the Euler solution method. And by the way, notice that this is not using the standard notation of delta t times f, evaluated at t and y, but I am breaking it up into the fact that the system of equations is actually given in terms of f, is given in terms of the matrix of coefficients and the vector g. So this is how I am actually resolving that. So at the end of these, if I print y exact, I'm going to get these 11 elements, and if I print y Euler, I'm going to get this elements. The y Euler is also a 11 by 2 array containing the 11 elements of the discretized time, of the solution over the discretized time, of the two state variable solutions. So this column should compare to this column, while this column right here should compare to this column. We'll do that quantitatively and qualitatively just later. Now, the same way I implemented these for the Euler's method, I can implement it for the modified Euler's method within. So I start by looping over all the state variable solutions from 1 through k, and filling in the first element of the solution array with the initial conditions. And then I loop from 1 to the number of time steps, and internally I loop from 1 through k to the number of state variables. So I calculate k1 for each of the state variables, and then I calculate k2 for each of the state variables, and then I combine K2 and K1, also within a loop from K equal 1 through K, for each of the state variable solutions, Y1 and Y2. Okay, so the next time level is equal to the previous time level plus 1/2 of K1 and K2. So again, I can print the modified Euler right next to it. So if I print modified Euler, why have the modified Euler? I get the same thing, an 11 by 2 array that has the approximation for each of the time steps of each of the state variables. Then I can do the same for the Hoynes method, the same exact process for the Hoynes method. As you can see, it's just I loop from 1 through K to fill in with initial conditions, and I loop from 1 to N to calculate, to approximate the values at each of the time steps. And within each of the time step, I have internal loops from 1 to K to calculate K1, and then the corrector K2 from 1 to K, and then I combine 1/4 of K1 with 3/4 of K2 to approximate the solution of the next time level. And then I return Y as the Hoynes method. And then finally for Runge-Kutta, I do this 4 times. 1 predictor K1, 3 correctors K2, K3, K4, and all with these internal loops to calculate for each of the state variables. And then I combine 1/6 of K1, 1/3 of K2, 1/3 of K3, and 1/6 of K4 to approximate the solution of the next time level. Now I can visualize this. So I've already created a plot here over the time from 0 to the final time 2. The red one represents the exact solution. Okay, that's why I have a continuous line. While the symbols represent each of the numerical solutions. The blue squares represent the Euler solution. The green diamonds represent the modified Euler solution. The magenta circles represent the Hoynes solution, while the triangles, I think these are purple triangles, represent the Runge-Kutta solution. And as you can see, that at least qualitatively, they look to be the more accurate as compared to the exact solution. But this is the exact solution 1. I'm stating K equal 1. So notice I am evaluating every one of these 4 vectors. I'm sorry, 5 vectors, the exact, Euler, modified Euler, Hoynes, and Runge-Kutta at n with respect to all the time values indexed by n at K, which denotes the state variable. So it's basically Y1. If I wanted Y2, then this is how they compare. As you can see, again, the triangles do the better job at actually approximating the solution. And as you can see, those squares are actually all over the place. They don't do a very good job of approximating. They overshoot and then they undershoot the solution. Especially a solution like Y2, which seems to be non-monotonic. It grows and then it decays. The Euler's method is going to have a hard time trying to approximate that. So let's stick with K equal 1 first and see what kind of quantitative errors I got. The residual for the Euler's method is 7.43%. The same way that I defined the residuals last time, with the only difference, remember that the arrays are now starting at 1 instead of at 0. So I am adding adding the squares of the differences from 1 to n plus 1, dividing by n, taking the square root of that, and then dividing by the maximum of the exact solution of the K state variable. I can access the entire second column or the first column, or I can access a specific column of an array, of a 2-dimensional array, by using Control 6. So this is y dot x, Control 6, which accesses a column, and I am accessing the kth column because that is the one that I am visualizing over here. So I'm basically normalizing the standard deviation by dividing by the maximum span, the maximum minus the minimum value of the exact solution. So I get a good non-dimensional quantification of the error. And then I'm using a percentage as a unit to denote that this is the actual quantified error or residual between the exact and the Euler solutions. You can see, obviously, the Runge-Kutta is much better than the other two. The Hoynes and the modified Euler seems to be almost identical. And the Runge-Kutta seems to be orders of magnitude better. But more importantly, let's look at K2 first. If I change to the second state variable, I should expect the Euler to give me a very large error. So if I update that with F9, I get 26% error. That's the blue squares. If I update the modified Euler, I get 11%. Points, I also get 11%. And 0.448% for the Runge-Kutta. Much better, again, orders of magnitude better. I don't know why the Runge-Kutta, the modified Euler and the Hoynes seem to be given identical solutions. That's very unusual. Let's see if I am not renaming the vector. So this is Runge-Kutta, this is Hoynes, and this is modified Euler, so it's fine. These are linear system of equations. So in a linear system of equations, the Hoynes and the Runge-Kutta, the Hoynes and the modified Euler will tend to actually give exactly the same solution. All right, so if I change the level of approximation, or the resolution of the discretization by a factor of 2, making the delta t exactly half the size of the delta t before, I should get half the error in the case of Euler. So Euler, see, still overshooting and undershooting the exact solution, but it's doing it a little bit better than before. So if I update this error here, now it's 9%, and if I update this, I should get 100 times better error, 2%. Oh, I'm sorry, not 100 times. I modified delta t by a factor of 2, so this should be 2 squares. It should be 4 times better. So from 11, it went down to 2. Again, that's not 4 times better, but it's within the order of magnitude of 4 times better. Remember, this is error bounds. Well, this one should be 16 times better. So if I update this value, I had 0.4, now I have 0.02. So it's roughly 20 times better, which is in the order of magnitude of 16, as expected. So if I then change this number to, let's say, 100, I should see a better quantitative solution, as expected. The blue squares are still having a hard time catching up. So if I update this, I get 1.6. If I update this, I get 0.05. If I update this, I get 0.05. And if I update the Runge-Kutta, I get 0.000024. So 2.4 times 10 to the minus 5% error between the two solutions. So residual between the two solutions. Again, that is in solution 2. If I look at solution 1, this looks very good. And if I update this, it's already updated for me. 3 times 10 to the minus 6. Well, this one is it's already updated, 0.013. So this is how the implementation of the solution, the numerical approximation schemes that we formulated for single ODEs and single initial conditions now can be extended to multiple systems of multiple coupled systems of ordinary differential equations and initial conditions. And so it's a very simple extension, and as you can see, it does a pretty good job of approximating, at least for these cases where we actually managed to get an exact solution, which, remember, is very limited. This exact methodology, or the analytical method to get exact solutions for a system of ODEs, is extremely limited to homogeneous and constant coefficient type of system, linear system of equations. So this is it for today. I'll be posting this video and this spreadsheet on Canvas, and I'll see you next time.